Previously, we talked about the chambers and the anatomy of the heart. We saw that there were four chambers. Here's the right atrium, the right ventricle, the left atrium, and the left ventricle. We talked about how most of the heart is really myocardium, that is muscle. However, there is actually a conduction system, which is actually nervous tissue inside of there. And this is responsible for distributing electrical signal. We call it depolarization. And this is like turning on a light bulb. And so when depolarization passes by parts of the heart, the muscle then contracts. This squeezes the blood, and that's what moves it from chamber to chamber. Let's go ahead and draw a picture here, and we'll label it. And let's go ahead and highlight the parts of the conduction system here. So I'll just go ahead and start with a color here. And so it starts up here. This little piece here called the SA node, sinoatrial node. This is also called the pacemaker, Let me write that down here for you so that you remember. Well, we don't need such a big font. Let's get a smaller font. Pacemaker. And you may have heard about people who lose the ability to get a rhythm going in their hearts, and they have to have an artificial pacemaker put in there. The pacemaker spontaneously creates an electrical signal, so it doesn't have to be attached to anything. So if you take a heart just by itself, unattached, it'll still keep beating for a while. So this electrical signal comes and starts right here. This is what we call myogenic material, myogenic. And myogenic means muscle that stimulates itself, myogenic. Okay? So the signal starts over here, and then it goes down in two different directions. The major place it goes is down here, so it goes across the right atrium and goes to the bottom of the right atrium, and then it hooks into another part of the conduction system here, which is called the AV node. And the purpose of the AV node there is actually to slow down the signal. So let's write that down here so we remember. So it slows down the signal. Slows the signal. Okay, what's going on here? Well, first of all, when the electrical signal goes from the SA node to the AV node, it causes the contraction of the right atrium, which then pushes blood into the right ventricle. So it's being squeezed. Now, at the same time, what's happening is that signal is also going off here to the left side. Okay? So it then causes a depolarization on the left side. So what you can see is that the right side actually contracts just a little bit faster than the left side. So we get a certain rhythm, and that helps to actually keep the blood moving in a unidirection. Now, why is the signal slowed down when it gets down here to the AV node? And the reason is that blood physically moves a lot slower than electricity does. So you want to give it time to get all the blood into the right ventricle before you go ahead and depolarize it and contract it. Or else if you squeeze the right ventricle, there wouldn't be enough blood in there and you wouldn't have much cardiac output. Where's the next place that we go in the system here? Well, then it goes down right to the top of the septum, and this place right here is called the bundle of His. The bundle of His. Okay? And the purpose of the bundle of His is to separate the signal into a right and left signal. So now it's evenly going to go down, part to the right and part to the left. So we get the signal that goes down around the septum and the myocardium wall here, over on the right side, and at the same time goes down here to the left side. And that then causes a depolarization of both of these guys. And these fibers that it's coming down here, these fibers here and these fibers here, are called the Purkinje fibers, right? Purkinje fibers. And that causes the two ventricles to contract and to squeeze blood into their direction. So blood moved this way, then it moved this way, and then finally when we squeeze the ventricles, remember, it pops up the top of the heart like that. The same thing happened here, here, and then blood squeezed and went up to the top like that. Okay? So this is the conduction system, nervous tissue inside, and it is spontaneously contracting. Now, we'll talk later on about how the SA node here is hooked up to the nervous system of the body so we can influence it and regulate the heart rate, but we'll talk about that another time. Now, typically when you go into the hospital or the doctor or whatever, they put those little stickies all over you there, and they do a test called an EKG, which stands for electrocardiogram. Let's just call it an EKG. Terrible saying, electrocardiogram. What that tells us is the electrical movement, how depolarization is happening as electricity moves throughout this conduction system. And if you hook it up to an oscilloscope there, you see one of these readings. You always see it in hospitals going boop, 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 like that. And you see 3 different waves. The first wave is called the P wave. The second wave is actually called the QRS wave. So there it is down there. And it's because it's got 3 points, the Q, R, and the S. And the third wave is actually called the T wave, right? So you got the P wave, the QRS, which is this really tall one here, and the T wave. Now, don't be concerned if you go in there and you say, gee whiz, I'm looking at an EKG and it doesn't look, as big and tall as it should be. Size has nothing to do with anything. It's measuring the direction of things like vectors, so don't worry about it. Now, what are they looking for in EKG? Well, the first thing you're looking for is obviously all 3 waves, right? You want to see P, you want to see QRS, and you want to see T, and you want to see them in that direction. You don't want to see extra waves. You don't want to see a P and then another P and then a QRS and a T, and you don't want to see a wave missing, right? And the other thing they're looking for is they measure the distances between the waves, right? So they would measure the distance between P and R, and they'd measure the distance between S and T, so forth, and the distances tell them time. How do they know time? Because the paper that they're recording it on is measured. Typically, you can see here, what do they got here? 5 millimeters is equal to 0.2 seconds. So that means if we count the number of boxes, right, we can actually figure out what the time is between the waves. And there are averages that we expect of people who have normal heart beats. So if you calculated, like, say, the distance between this R and another R, right, that should be 1 beat, and you could tell what somebody's heart rate actually was. This is called an EKG. So the waves, once again, are the P wave, the QRS, and the T wave. Now, what do those waves mean? Well, the P wave occurs when the electrical signal is going from the SA node, right, to the AV node, okay? This is atrial depolarization. The QRS wave is where it's going from the AV node to the Purkinje fibers, right? So it's going around the 2 ventricles, right? Purkinje, yeah? So that's causing then ventricle depolarization. And the third wave actually happens when the electrical signal is starting to turn off and actually is heading back to the SA node. I know it's not connected, but it actually, electricity just kind of goes like a wave and works its way back there. And that's when the ventricles actually repolarize. So they're not being stimulated any longer. They're not being depolarized, they're repolarizing. Now, you can go ahead and relate these guys to what is physically happening while the electricity is moving there. So in the P wave, right, that is atrial depolarization. What is happening? The atrium is then, at that point, contracting. And blood is moving out of the atrium into the ventricle. What's happening in the QRS wave, right? That's where the ventricles are contracting. And finally, what happens in the T wave? That's where the ventricles are relaxing. They're not contracting anymore. They're not being stimulated, so they relax. Now, you may notice there's somebody missing. When is the atrium relaxing? And the atrium would be relaxing at the same place that the ventricles are contracting, and so that wave actually is hiding behind the QRS wave. So if you go back here, this wave right here, this is when the ventricles are contracting, but it's also when the atria are relaxing, because blood was squeezed into the ventricles, and what happens is when the ventricles squeeze blood, that valve behind them closes, right? So that blood has to move in one direction out of the ventricles, and the atria go ahead and relax. Now, we've seen what it should normally look like. What's going on here? Well, we can clearly see the nice QRS. That looks pretty good. But it's starting to look pretty rotten here about the P's and the T waves, right? I can barely see the P waves and the T waves. Doesn't look like a very good pattern here, right? You can also see that what's going on. Oops, what happened here? Hey, it looks like we missed a whole QRS over there, right? Now what's going on here is atrial fibrillation. In other words, for some reason the atria are being overstimulated too fast and the rhythm has broken down. Now that's serious, but it's not fatal. What's really serious though is when we get problems into the ventricles. Now this one here is ventricle tachycardia. What does tachycardia mean? It means for some reason they're racing. Things are just going too fast. And so we see there's the P, there's the QRS, and the T, wow, is actually hidden somewhere in here because you're moving along so fast there really isn't time to have a good T wave. This is getting to be more serious, but the real problem, the one that we most hear about all the time, is this guy, ventricular fibrillation. Fibrillation is where you have a total breakdown of the rhythm in the ventricles. Now the ventricles, remember, are the guys who are supposed to be squeezing blood out to the lungs and to the rest of the body. Wow, I don't see any waves here. You got a total breakdown here. This guy basically is having a heart attack. This is really bad. So this is going to kill you here when you have a total breakdown because you're not delivering any blood carrying oxygen to the body here. So what do you have to do? Well, what you have to do is get in there real fast and reestablish the rhythm to get that EKG looking the way it should be so that we get blood. And how do we do that? With a defibrillator, or what's called an AED. We have a lot of these actually around the school here. So what do you do here? You go ahead, first of all, and you apply electropads to the chest. Okay, so the heart is going to be around here. The heart's around here, so we put these two pads or plates right on top of the chest. And then you turn on the machine here, right? Now the cool thing is that the AED will determine if indeed the heart has stopped and you need to do a shock. It won't let you do it if this person really hasn't gone into defibrillation. So it'll tell you, yes or no, if you can do it. If it says yes, then you go ahead and press the button here, right? And you deliver a shock to try and restart the heart. It's like hard booting a computer, just turning it off and turning it on again. And if you were successful, it should then reestablish the normal rhythm of the heart.